Hello, my name's Josh, and today I'm going to talk a bit about my individual project, the automation of RBAC permissions in Kubernetes clusters. First of all, I'm going to talk a bit about the background of the project, and then I'm going to talk about the problems that I found inside Kubernetes in terms of the RBAC. I'm going to talk a bit about what my solution is going to be to that problem, how I came about that solution, why it's the best. I'm going to talk a bit about what I've done so far in terms of the project, and then finally I'm going to talk a bit about what I've got left to do in the project. So first of all, what are containers? Containers are a piece of software or components which are used to provide an operating system level of virtualization. Just like virtual machines, they provide isolation from not just each other but also the host machine. Now, unlike virtual machines, which use hypervisors in order to facilitate this, hypervisor being a piece of software providing operating system management and monitoring of each virtual machine's operating system. Instead, containers use the host operating system to provide operating system services, things like input, output, memory, CPU, that sort of thing. So there are a number of reasons why containers are quite advantageous. Firstly, provide portability, since they have the ability to package all the needed software which you'd need to run containers in service, for example, to run specific jobs. It can all be packaged into one. Secondly, they're very lightweight and efficient. The resources that they use are flexible and they can change during runtime. Things like memory and CPU, unlike most virtual machines, they're not a fixed value. And then thirdly, they're very, very quick to start up. So unlike virtual machines, which take a long time to start up, they're very, very quick. Now, containers have become very popular, especially with the release of a piece of software called Docker, which is essentially a container management and deployment software. It gives the user a lot of granularity and control over the containers and how they're deployed. Now, however, in order to deploy any kind of large-scale system of containers, more software is really required. Otherwise, a lot of this has to be done by hand. It can become very difficult to scale any large amount of containers. And this is where Kubernetes comes in. Kubernetes is a piece of software which was originally designed by some Google engineers who had previously worked on some internal software very similar to Kubernetes. But however, the project is now completely open source, and it's one of the largest active projects in GitHub with over 1,500 contributors. Very briefly, how does Kubernetes actually work? Well, as you can see on the slide, I've got a diagram of the topological view of the Kubernetes architecture. And essentially, Kubernetes runs on a paradigm of a desired state and a current state. You have the current state of the cluster, and then usually a desired state, a user-defined desired state. And it's the master node's responsibility to converge the current state into the desired state. Now, you also have worker nodes. Worker nodes contain pods. Pods are a logical collection of containers, and these containers are where you're actually running your deployed application. The worker nodes can communicate with the internet through the kube proxy, and then the worker nodes communicate with the master node through the use of the kubelet talking to the API server. In order for Kubernetes to facilitate authorization of components or users within the cluster and limiting or allowing different subjects to perform different actions, it implements a system called role-based access control, or RBAC. And this can best be explained by the second diagram on the slide. Here, for example, if we take role A and B and C, and let's call them, say that they give the ability to create a pod, delete a pod, and list pods, respectively, and then subject 1, therefore, is now bound to role A, B, and C. Therefore, subject 1 is now has the ability to create, delete, and list pods. Although the current system works well in that it provides cluster administrators with a large amount of granularity and control over the permissions of each subject within a cluster, I've identified 3 main problems that I find with the current system. The first problem is administration. Currently, for any cluster that scales to a large size, there's a large administration cost to ensure the permissions of each subject within the cluster are set correctly. As this all has to be done by hand, it's very prone to human error. The second problem that I've identified is the fact that there's no easy solution to implement dynamic permissions of subjects within a Kubernetes cluster. A use case for this, for example, is the fact that there's a package manager-like system in Kubernetes where a client called Helm will communicate a deployment to a server running on in the Kubernetes cluster called Tiller, and then the Tiller will go off and execute this deployment in the correct way. Now, for Tiller to be able to execute this, it needs to have admin permissions. However, after it's completed to execute this deployment, the Tiller will reside in this elevated permission state, where if it could be exploited maliciously, it could be devastating for a cluster. The third problem that I've identified with the current system is there's no easy way to implement impersonation of one subject to another. For this, a use case for this, for example, is if a new developer joins an organization where their permissions need to match their colleagues, someone has to go through by hand and match every single role and then add a new role binding to this new developer. There should exist some solution where you can get one subject to impersonate another very easily. In order to solve these problems, I've been developing a piece of software which takes in rules, which once their triggers have been met, executes some RBAC event inside the cluster. An RBAC event is defined by an origin subject and several destination subjects, where both origin subjects and destination subjects can be any one of a service account, group of users, or a user, or in the case of an origin subject, also a role. Once the RBAC event has been triggered, all destination subjects will have their permissions matched to the origin subject. This obviously immediately fixes the impersonation problem, as all destination subjects will be impersonating the origin subject. Triggers are defined by not only time events, but also events happening inside the cluster, for example, pods being created or deleted. This fixes the administration problem, as for example, service accounts being added to the cluster can automatically have their permissions assigned to them. Also, it fixes the dynamic permissions problem, as it means that subjects can have their permissions changed according to some predefined rule defined by the user. In order to implement this solution, I have chosen to create an external component towards Kubernetes itself. I have chosen not to change Kubernetes code base itself, because it means that end users will have to use my edited version of Kubernetes every time Kubernetes has been released. This not only adds extra complexity to end users, but it means that every time Kubernetes releases a new version, I have to edit the code base myself. For my software, I've chosen for my end user to communicate with the software over the Kubernetes API server. I've not chosen any local communication system, such as local filing system, as this can cause problems with reading and writing from the data at the same time and administration of the files. Also, inter-process communication, as usually a user would be working with the Kubernetes cluster remotely. As well, it would be ideal for my software to be running inside the Kubernetes cluster itself, so this wouldn't be possible. Currently, my software implements a new resource type within the Kubernetes API, which is what the user is using to send rules to it. They are then stored as objects of that resource type, which is what my software is listening to. When new objects are added to the API, my software will then parse those objects, and then it will wait for those triggers to be met, defined in the rule, and then once they have been met, it will execute whatever RBAC event was defined. Currently, my software implements all the kinds of origin and destination subjects, as well as many triggers, and these are being executed correctly, and the RBAC permissions are correct. Although in its current state, my software works and is usable, there are some more things I need to do before I finish my project. Firstly, although I implement a number of triggers at the moment, in order for my software to be feature-rich and desirable by users, I need to implement a further number of triggers for the rules. Secondly, I would like to implement a feature to ensure that the time that the user is using is correct. Since we're using time-based triggers and we're dealing with security, it is important to ensure that the time that the computer is using is correct. So this will be using some kind of mechanism such as NTP. I still need to implement further testing, although I have some unit testing at the moment, especially dealing with security. It's quite important that the program is correct. So I'll be expanding this unit testing further out through the program, as well as using end-to-end testing to ensure that all units work together as intended. I will also be implementing failure recovery in that if my software for whatever reason crashes or becomes offline for whatever reason to the API server, then when it reconnects again, it is able to return to the state it was before, to ensure that no rules are lost, and the state of RBAC permissions inside the cluster isn't in a state that's unintentional or undesired. Finally, for the end user to be able to use the software at all, documentation is very important. So I'll be spending some time to make sure that I write useful documentation to guide the user in creating such rules, so they can use the software correctly and efficiently. Thank you very much for listening to my video on the automation of RBAC permissions in Kubernetes clusters.